Hello, I'm Marco De Fazio, Strategic Marketing Manager for the region Americas. I'm here presenting a new kit that we built for education. It's a Rotary inverted pendulum. We presented the prototype of this kit at CES 2019. Now we have the final version. This kit has been developed by our partners at UCLA, and it's been built by our partner company GH in Italy. And I'm presenting the final version here that will be available for purchase in Q4 2019. The system is very simple. It's meant for teaching, so it's not meant to present the best performance we can get with our parts, but it's meant to offer a way to students to experiment with motor control and control system. It's based on the STM32 open development environment and the Nucleo boards. The system is built by this whiteboard, which is an STM32 Cortex M4 microcontroller, a stepper motor driver. Then we have a rotary encoder here on top of the system, and we are using a stepper motor, so only one motor to actuate the system. All these will be part of the kit that you can assemble. The kit will include the mechanical parts, the frame, the motor, the encoder, the pendulum itself, and the electronic boards. So the way this works, it's very simple. We have only 1 degree of freedom. The rotary axis here. We are completely free in this direction. And what we want to do is to try to keep the pendulum balanced by only rotating this. This is a very well-known control system problem that is not that easy to solve, and it's solved in real time on the STM32. We also have a connection to MATLAB. We can show the real-time performances of the system on the screen. And when we start this, we can look at the screen and see what is actually happening. So what we're seeing here, it's the rotor angle. So actually the direction where the motor is pointing to. We have the pendulum angle, so the position of the pendulum. The command we give to the motor, this is the target position that we give to the motor, and that's actually the actual motor control signal. So every 20 seconds we give a command to the motor to move faster to a new position. So this is a 16 degrees step in one direction, and on top of that we sum a sine wave for the motor to sweep from plus minus 90 degrees. So this makes the system more compelling to solve, more complicated. We can actuate the system in different way, and we can do this in real time by switching, for example, the microstep per second speed of the motor. This will make the motor faster to move to a target position, but a little bit more noisy. We can also use an adaptive firmware where we go in the low-speed mode where the noise is reduced significantly. But when the command to go to a particular position occurs, then we move it very fast, and then we go back to the original firmware, so where we have less vibration. This is a pretty sophisticated version of the firmware. The students that will use a specific curriculum designed around this system will start with the basics of motor control. They will start to solve the pendulum when it's off. This is a stable system. Then they will start to solve with the basic PID control loop the unstable system of the pendulum kept upright, and then they learn from their more advanced control system, like the one we're showing here, which is based on state space and LQR. I want to say that we are particularly proud of this system because it's the first time that an educational tool for control system is based on an unstable system. And that is made possible by running the firmware in real time on a microcontroller that is very accessible because it makes use of a very open ecosystem like the STM32 ODE. Our educational tool is part of a larger ecosystem where we can collect our offering for education. We have an almost complete ecosystem for embedded system. We start from low-level, register-level firmware programming in assembly language with a drone kit. This is already available, and it's been developed by the University of Maine. Then we have our sensor tile. The sensor tile is a small board embedded sensors, Bluetooth, low energy, and a microcontroller. We have a complete set of instructions building a full curriculum for embedded system for both freshmen and seniors at universities. And we are expanding the sensor tile curriculum on IoT with artificial intelligence as well for next year. On power electronics, we're starting with this new kit on a motor controller control system, but we're planning more implementation, and this will make ST the perfect partner for a university to develop their curriculum and their teaching platforms. You can find information on st.com, look for educational platforms, and you find everything you need.